Swayam Prabha. Digital India. Educated India.
So when you have random distribution, we talked about volume fraction, which is take a volume and you can ask how much of what fraction of the volume that the particles occupy. But there are other ways of measuring how these particles are distributed, how uniform that distribution is, are there clusters. Again, why do we care about these things? Because later when we do models, we want to know, if we develop a model, we got to know whether it applies for uniform distribution of particles inside, or if there is clustered, we may have to modify the model. Okay. I must admit that the existing models don't ask these kind of detailed questions. You just take the model and you run with it. You run your code, etc. Often the results aren't satisfactory, but we are here to learn more, think about new things, and do better than what we have been doing. Okay, and that's why I'm bringing these up. These are realistic questions. They do come up, and people are developing better models using these ideas, and I want you to expose you to those concepts. Okay. So knowing whether a distribution of particles, how close to uniform it is a very important question. Okay. So one of the things I want to talk about is that how do people describe this kind of distribution? Okay, I said that you have this square region and you're throwing n number of particles in there, and I said, so theoreticians start at the grand level, things that you cannot do, but just you can think about them. Okay, this quantity Gn is like that. Okay, it says it's like mother of everything that you want to know about this distribution. Okay, so what it says is what's the probability of first particle being in x1, second particle being in x2, and the nth particle being in. It's a one heck of a statistical quantity. Okay, you will never be able to compute it, but that's the starting point. We say that, hey, there exists a mathematical entity, a probability that gives you where all the n particles are located. Okay. Now, since it's a probability, the integral of this quantity is by definition 1. Okay. From here you can calculate what's the probability of all the n being in one corner, or all the n being uniformly distributed. All that information is in this quantity. Now this, I said, is so hard. Okay. So what you instead ask this F1 is simply saying, I don't care about all the n particles, but I will tell you a position x1, and you tell me what's the probability of finding a particle there. Okay, and I don't care which of that n particle going to appear. So it's a much simpler question. So this F is related to volume fraction, because it will tell you what the probability of finding a particle given any spot. If it is 10%, then the average volume fraction there is 10%. Okay. So the way to get this from this mother of all statistical quantity is you say one particle is in that location, and you say I don't care where the others are. So you integrate over all the other 2 to n, all of them you average out. Okay. And then I multiply by n, because I don't care whether the first particle is there, or the second particle is there, or the third particle is there. Any one of them can be there. So it's just a simple quantity. So F1 is the kind of quantity that we deal with. It's the probability of finding one particle at a location, whatever location that you pick. You can do a little better than that, and this is what is very important, which is the 2 particle statistic. So F1 is called 1 particle statistic. You just ask, you pick a point and you say, hey, what's the probability of finding a particle there? And F2 is, you have to pick 2 points and you ask a question, what's the probability of finding at the same time two particles, one here and one here. Because this quantity, this F2 is very important, because it tells you how particles are arranged in the neighborhood. Okay. So, when we are talking about later particle-particle interaction, quantities like this 2 particle statistics will become important. Now, you can go to 3 particle statistics and so on and so forth, but for now most of the time we will deal with only 1 particle statistics, and if you are a little greedy we may go to 2 particle statistics, etc. Okay. The 1 particle statistics is related to volume fraction. Now, when you know volume fraction, it does not tell you anything about the neighborhood in a direct way. For that you have to go to 2 particle statistics, whether the 2 particles are to the left, to the right, to up, down, all those, that neighbor particle-particle interaction can only be known through 2 particle statistics. Therefore, it is often very important. And this 2 particle statistics usually is given in radial distribution function. Okay. The radial distribution function is mathematically is the 2 particle statistics F2, the probability of 2 particles being at the locations x1 and x2, divided by 1 particle statistics for the first point and the 1 particle statistics for the second point. So, radial distribution function is a normalized quantity.
Accordingly, we want to switch over to the coupling average. So,
what is that?
Coupling. 1-way coupling, 2-way coupling.
This is a great question. Thanks for asking this. Here I have nothing to do with dynamics. This is like a marble. I throw marble. How do I describe where the marbles are? Whether it's no fluid, nothing. This is just trying to give you a big picture. How do I even talk about where the particles are? Now, of course, in a 2-way coupled system, it's changing over time, etc. So, I'm trying to look at if particles are randomly distributed, when do I say it's uniform, when do I say it's not, when is it clustered? So, that's the very simple minded thing. So, nothing to do with 1-way, 2-way, etc. Only particle. Now, it's interesting that 2-way coupling may change this radial distribution function. They may have some effect, etc. But I'm only talking about the kinematic aspects of how do I describe. Okay. Now, radial distribution function for point particles, and is perfectly uniform, it will be a flat function, the g of r. In other words, I have equal probability of seeing my neighbor anyway. So, this g of r, this g of x1, x2 is basically saying if I have a particle at x1, what is the probability of finding another one in a nearby point. And that in a perfectly uniform distribution has no preference, it is just uniformly distributed. Now, one of the things that I should tell you, maybe it's something that so I will get to that. So, here one way to think of this g in a isotropic case, this complicated thing will become in a isotropic is only a function of r. So, because of the symmetries in a isotropic multiphase turbulence, g is only a function of r. And what is this g as a function of r? Is simply if I have a particle at some location, what is the probability of finding a neighbor at a distance r away? Okay. That is a very important quantity. When you have random distribution of particles, you can calculate this radial distribution function, and it tells you how your particles are, 2 particle statistics is arranged, how your neighbors are arranged. So, this is a very important quantity to go beyond just saying what is the local volume fraction. In addition to local volume fraction, let us say volume fraction is 5%, that tells you that 5% of the volume is occupied by the particle. Then you can ask a question, how does the radial distribution function looks like, that tell you where your neighbors are arranged. Okay. And maybe if I erase this, you will see this picture, it will look like this. For finite size particles, this is how the radial distribution function will look like. So, the x axis is divided by the diameter. This is for a monodispersed system. For your neighbor can't come closer than one diameter. So your radius is r, and another particle comes. So your minimum distance is one diameter. It's interesting that when you have finite particle, the probability of finding a neighbor right close to you is 3 times larger. Think about that. And it goes down a little distance away, 1.5 diameters away, it goes down. So it has this kind of behavior. Now, you may think this is not very interesting, what's the big deal? But you know, when particles, when you're trying to calculate droplet collision, agglomerations, etc., what you want caring about is, I have a droplet, what's the probability of a neighbor being around at say 5% volume fraction? Average volume fraction is 5%. What this guy is telling is that very close to me, the 5% gets multiplied by 3. I have 15% probability being somebody very close to me. So that means collision rate is going to be 3 times larger. Okay. So this happens because of the finite size and finite volume fraction, and people do plot these radial distribution functions. So particle-particle interaction statistics, you have to think in terms of radial distribution function. It's a very useful quantity. Okay, so yes.
So can it be thought as a gradient of particles distributed across the domain or something like that?
No, it's not. Actually, great question. Suppose I have a big volume and I have uniform random distribution. At 5% volume fraction, particles are uniformly distributed. I take and calculate volume fraction. Everywhere, if I take a big enough volume fraction, we just saw earlier it's Poisson distributed. If the volume is fairly large, everywhere I am going to get, if the average is 5% volume fraction, everywhere 5% volume fraction. I do not have any gradient of volume fraction. This is 2 particle distribution in the uniform distribution. So particles are uniformly distributed. Even then, the fact that another particle can't overlap, so this ringing happens because of the fact that particles can overlap, so they push their neighbors. So the neighbors seems to be preferentially concentrated in a tiny little ring around them. Okay. So it naturally happens when you distribute. See, earlier slide I talked about 3 ways of creating uniform random distribution. Every one of them, when you create, the probability of seeing more particles at closer distance is higher. That's the natural phenomenon. Any other questions? So in other words, so the reason I go with these things is, we think uniform distribution is straightforward, simple, but it is nothing but simple, let alone non-uniform distributions. There is a lot of hidden complexities make the problem really hard. You have another question?
Yes, sir.
Yeah.
Sir, actually it is a graph on y-axis versus the radius or the diameter of the axis.
This is this distance r divided by particle diameter.
Yeah, so with radius, sometimes the probability is going suddenly down and then up,
Yes.
then down and then up.
Yeah, that's the way it is. So in other words, when you randomly distribute it, the fact that a particle has a finite size, it has a ringing kind of effect, sort of like interference. Okay, you know, grading patterns. So there are people studied this extensively. I'm no expert at this, but the fact that I know is that when you have random distribution and you put and you say, I have my particle, what's the likelihood of seeing neighbors? It arranges this way naturally. So I want to bring that to your attention because it's big. It's not small. Look at this magnitude is 3 times larger. Okay. So for collision statistics, it makes a big difference. So for example, rain formation, etc. People now understand that the rate at which collision occurs is far higher than what people originally thought, assuming everything to be uniform. It doesn't. These kind of small, what may look like small things, make a big difference on collisional dynamics. Okay. The other thing that will be very useful is what's called, how many of you know Voronoi tessellation? Do you guys know? Voronoi tessellation is nothing but, in 2D is easy to think of. So if you have particles, so here there are particles. So, what you look at is every particle you try to, so for example, you take this particle, he has one neighbor, he has another neighbor, this neighbor, etc. You look at all the closest neighbors and you draw your bisector and you put a box around it. So, in other words, everything inside the Voronoi volume is closer to that particle than anybody else. So, you can think of Voronoi tessellation tells you every particle's volume. Inside that box, that particle is the closest particle. So, this volume, every point inside the volume is closer to this particle. Now, you can see in a random distribution, every particle's Voronoi volume is not the same. If you had in a uniform grid, everybody will have the same volume. Now, you have different volumes. Okay, that's a measure of randomness, right? Create a million particles, and I calculate Voronoi volume of each of them. And let's plot all the Voronoi volumes and the probability or histogram. And you draw this, and this is for a volume fraction. It's got cut out. I don't know. It's about, say, 10% volume fraction. This is how it looks like. And by the way, this paper was written by Senthil Kumar and Kumaran, Professor Kumaran at IISc. Brilliant paper. Okay, so they calculated. They found that for uniform distribution, it follows what is called a 3 gamma distribution. Okay. So, what now we have a way to tell if you give me random distribution of particles and you want to know whether it is random, uniform random, or is it clustered. I say go first calculate Voronoi volume fraction. If you calculate Voronoi volume and you draw the plot, the histogram, and if it fits 3 gamma, it's uniform random. If it is clustered, in other words, some volumes are closer, some volumes are big, you will get a Voronoi volume fraction which will look like this, broader. Probability of tiny volumes, very large volumes is increases. On the other hand, if it is extremely structured, you will get like this, because everybody has the same Voronoi volume. Okay? So, here is a great way of telling whether something is uniform or not. Okay? You take your volume and you calculate Voronoi volume fraction, and you look at it, and you can say whether it's uniform, whether it's clustered, whether it is structured. Okay? Structured, sharp, and if it is clustered, some clustering, some open spaces, large open spaces, then you will have a broad distribution. Voronoi volume being very helpful. And here is a simple example. This could be fluidized bed. Many of you talked about fluidized bed. And you see all the particles. There are millions of them here on this one. And if the flow is coming, so this kind of instability you often see in fluidized bed. I don't know how many of you are familiar with that. So, these red regions are high volume fraction, and the blue regions are lower volume fraction. Actually, this is not fluidized bed, so I lied. So, what really you have in this case is this green line is the shock, and the particles are passing through a shock in this case. The particles, so you know that on the other side of the shock, the gas becomes high density. So, same thing happens for the particles also. So, in other words, the velocity is low, but the density of the gas increases. But what you see here is particles. The particles come at 10% volume fraction, uniform distribution. Why? So, if I measure Voronoi volume for that 10% volume fraction, the purple histograms is what we actually measure. And this yellow line that you see is what Kumar and Kumaran's 3 gamma theoretical prediction. And you can see it's spot on. It's a wonderful. So we now know, when I ask my student, go calculate Voronoi volume distribution. And only when they compare, I know that they have uniform distribution. That's really as good. Okay, that's one of the really nice papers. Now, when these particles come out of the shock, now the gas is going faster than the particles because Stokes number is greater than 1, because gas changes instantly. Time scale is nanoseconds. Particles, even 10 micron particles, are now too sluggish. So you see, it takes a while for them to get to the new velocity. I am not plotting the velocity, so it is trying to catch up to the post-shock velocity. And there is therefore drag. So what happens is that volume fraction dependent drag, which we will see later on, creates instability. So when you have volume fraction dependent drag, these particles, just like in a fluidized bed, when you have air going over particles, it will separate into layers of many dense particles, empty region, many layer of dense particles, and that's what you see here. Now, what would the Voronoi volume distribution here look like? So that's the question, and that is the plot here. Okay. Now, here the volume fraction, the average volume fraction here increases to 20%, because just like the gas gets denser, particles also get denser. Therefore, this yellow line, which is, had it been uniform, it would have been this line. This is for 10% volume fraction, the 3 gamma distribution. This is the 3 gamma distribution for 25% or whatever volume fraction. But because of the fact that we have non-uniformly distributed particles, there are clustering, there are high regions of very small volume fraction, and there are regions of very large volume, open spaces. Okay? So in other words, what we measure here, the Voronoi volume distribution, is quite different from 3 gamma distribution, and therefore we know that this thing is clustered. So this is one example of knowing how you can use Voronoi volume fraction to decide whether there is structure in your distribution of particles. Okay, what that matters is that, again, as I mentioned several times, if you are now going to describe the drag on this kind of setup, you will have to know that the volume fraction is not nice and uniform. It doesn't follow Poisson distribution. It doesn't follow 3 gamma volume Voronoi volume distribution. So that's just a nice example I thought I will share with you.